Hello and welcome to everybody. Today in this class we will discuss about experiment 4 called hyperspectral imaging. So first of all we had learned about the principles of colorimetry and how color or color perception is important in the analysis of different experiments and different samples. Here we will be learning an advanced technique of color analysis, that how we can use hyperspectral imaging in order to analyze the samples or the data in a much robust and in a much wonderful way. So first we'll deal with the basic concepts of hyperspectral imaging. So if you talk about HSI or hyperspectral imaging, basically it's an extremely powerful and a non-destructive technique. Now we know that non-destructive technique means when the sample to be analyzed is not destroyed at all. The sample remains intact and we capture the visual information or the spectral information of the data. Now, the most important thing between colorimetry and hyperspectral imaging is that in case of colorimetry, we are only concerned about measuring the parameters L star, A star, and B. So that is the C, I, E, L, B parameters. But in case of hyperspectral imaging, the major wonderful thing is that whenever it captures an image, it analyzes the image pixel by pixel of the particular image, which means suppose if there are 50 pixels in an image, it will analyze 50 pixels itself, which, and in other words, it will try to generate the spectra of the 50 pixels in a particular image, and it will then collate all the spectra, and then through the different learning model techniques like artificial neural network and different other techniques, we can then generate a beautiful hyper spectra. Why it's called hyper? Because we are trying to generate a hyper activated information or a wonderful or a better information rather than the normal reflected spectra that we discussed in our on experiment 3. Now, what is the major point or the major importance of this particular technique is that in case of normal traditional or conventional RGB cameras, we can only capture the color bands pertaining to the three colors, right? But in case of hyperspectral imaging, for multiple colors, we can capture in continuous spectral bands, which means a three-dimensional data set is created, and that is called a hypercube. As you can see from here in this image, this particular box is called a hypercube. Why? Because it gathers the spectra from all the pixels of the images, it collates, and finally it creates a 3D space called hypercube, and that is basically called the unique spectral signature. So whenever we talk about spectroscopy, we try to deal with the nature of the samples, and every sample has a distinct and a unique spectra, which is called spectral signature. In other words, in chemistry or in biological science, we call it as a fingerprint. And thus, this particular hyperspectral imaging technique helps us to analyze an object in a much broader and a much detailed way, as you can see from particular figure. Suppose if you are taking the image from this particular point, let's say in the soil, or from a colorimeter, let's say LAB, you will only be getting surface parameters. But the interactions between the surface parameters, how the surface molecules behave, these you can detect or understand more clearly by using this hyperspectral imaging, because it uses the technique of spatial mapping. And this was driven basically by the idea of NASA, where Everest was when Everest was conceptualized, and this basically had fostered the creation of hyperspectral imaging technique. Okay. Now, if we talk about these three particular imaging systems difference, first we deal with the RGB image system, then we have the multispectral, and there's a hyperspectral. So here it's very simple. In RGB imaging, we know only the colors that can be perceived by the human eye, mainly red, green, and blue. They only focus on just three colors, and therefore the spectral resolution, which means between two spectra, how much difference you can generate. There is the minimum distance between the two spectra, that is low, which means we will not be getting good quality data with RGB imaging. Then, to alleviate this particular problem, we had the multispectral imaging, which enhances this RGB imaging basically, or it improves the RGB imaging by helping it to capture typically about 36 images basically, and having broader non-contiguous bands. Non-contiguous bands means when the spectral bands are not floated together and they're not continuous in nature, they are discrete in nature. Now, this is important because this was first conceptualized, so this was important, but we couldn't get a three-dimensional outlook or information using a multispectral imaging band. In hyperspectral imaging, if you see, it surpasses this, it basically outperforms both this RGB imaging and the multispectral imaging. Why? Because it has a capability to generate narrow continuous spectral bands. If you see from here, you will not be able to distinguish the spectral bands because these bands overall will give you the hypercube, which will help us to understand the overall morphology and the particular morphological characteristics of the samples, and especially at each pixel, which means how much volume of data is analyzed by hyperspectral imaging. You cannot imagine. So much volume of data is analyzed in one single click or one single go, which means this is much more powerful than the other spectral systems. Yeah. Then we have the additive function. You can just read the slides. These are some of the characteristics and differences. Then we come to the mechanism of action. This is how hyperspectral imaging technology works. So first of all, for hyperspectral imaging, we have four different scanning systems. One is called the spatial scanning, then we have the spectral scanning, then we have spatiospectral scanning, and the snapshot imaging. Okay. So these are some of the things, and this is called the lambda, which is basically your spectral resolution. So the spatial scanning, the first initial stage HSI systems were based on whisk broom scanning. Whisk broom scanning means, suppose let's say you have a scanner and you are keeping a scanner in the hand. So what will do? The scanner will try to scan the entire image of the hand in one go, and then what will happen? Then in the backend process, your hypercube data will be generated pixel by pixel. Now the problem here is that when the particular image is being converted to a hypercube, there might be chances that some things are lost. Some information is lost in that part, which is a great disadvantage in case of a scroll image. Okay. Then what happens? Then we have the spectral scanning, which is called a staring or tunable filtered imaging. First of all, what happens is that it first what it does, it captures or it takes the 2D images of a particular on one wavelength per time. This is very important. At a particular wavelength, at a time, it will take the full image, then it will try to tailor or tune the bands, and then assemble the hyperspectral data cube as a stack of narrow spectral images. If you see here, see, these are now stacked together, but narrow stacking is there, which means the clarity or the amount of data that will be generated will be much more accurate here. And then we have the spatial and spectral, which is combining these two together, which captures an entire line of pixels in one exposure, then building the data queue line by line as the sensor sample moves. Now the principle, you will ask me, so the principle is same. Definitely the principle remains same for all these three, but the clarity or the resolution continues. Now you will ask me that, sir, why the entire image is taken at one go? Now, if the image is taken in parts by parts, then how will the image be processed and the hypercube be generated? That's the important point part. And this one is the latest part. This is called snapshot imaging, which means that an image will be captured, and then and there, at the time itself, your hyperspectral image data cube will be generated. This is much more costlier systems as compared to these three. And then we have a novel workflow. This is basically a lab developed hyperspectral image system that was developed by our senior, Edward Sahu. So in that part or in this context, we'll try to explain what is the exact workflow First of all, what happens? This is your CMS camera. What happens is that, let's say this is an object. Light falls on here, and based on the Cartesian coordinates, your light is being captured. Okay. After that, this captured rays of light goes to a computing platform where we basically have a pixel by spectra. You understand that in each pixel, if you 1, 2, 3, 4, if you see these pixels, let me just point on and show you. Okay, let me show it with a pen. If this is your pixel 1, let's say pixel 1, pixel 2, pixel 3, pixel 4. So it will try to generate the spectra of all the pixels one by one at a time. That will help us to analyze how the reflectance intensity of the image is varying pixel by pixel, which is not possible in the case of normal RGB cameras or in the case of normal colorimeters, as we discussed in the last class. So after the pixel vector is generated basically, then with the help of an algorithm, we try to create this pixel wise data. See, a novel software driven method, it captures the spectral data at each pixel. Okay. Okay. And then we have this spectral prediction. Spectral prediction means where this particular pixel spectra will be converted into a tabular form with the help of a model called ANN model. Try to understand that what the values are. These are basically values. This is a pixels, and these are values basically of each and every wavelength. Now we already have discussed why white or black calculation is there in the last class, and ultimately the wavelength range is 340 to 800 nanometer. And then what happens? We give a pseudo color image. Pseudo color means it's a type of computer generated color. Why? So as to make the people understand how the color intensity is varying, because we have to mimic the conditions that are being there in the real life, right? Therefore, using an LUT based color mapping, we use basically for the visual interpretation. And normalization is very important, because with normalization, you will not be able to generate this particular hyperspectra. This is called the hyperspectral images, and this is called the hypercube or HC. Here, okay. And these are some of the components of a system. First of all, we have the disperser devices. Then we have the detector arrays. Then to illuminate or to lighten up things, sources, optics and lenses, and data acquisition. And so you can just go through it and read. The most fascinating part of this hypersonic technology is that it is now widely used in different industries, in different labs for detecting food adulteration. Like for example, you have spices, and in the spices, suppose sand is mixed. You can definitely distinguish between the spice and sand using this hypersonic imaging. Also, we can detect this mycotoxin contamination. It is very important in terms of post harvest screening. Okay, PHS. Okay, post harvest. Why? Because after harvest, when the thing is spoiled, in naked eye we cannot see, but if we can detect at the early stage that food is contaminated or becoming bad, we can discard that, and we can also take measures so that the food spoilage is generally avoided. Okay? And also it's basically used in the remote sensing technologies, in industrial applications, and in medical and biomedical imaging. Recently now it has been started.